This video is going to be over second order linear non-homogeneous differential equations with constant coefficients. So remember, a linear differential equation is going to be of this form, and then this would be a non-homogeneous version because I have a function of x on the right-hand side. So we have to do two things. One, we need to find the complementary function, and then we also have to find what we're going to call a particular solution, and that's going to give us the g of x part when we plug in to our differential equation here. So back in another section, we were able to see that if we have this fundamental solution set, then this linear combination of those linearly independent functions that makes it a fundamental set of solutions, that when you plug into your differential equation, all ends up zeroing out, correct? But however, in this form, in the non-homogeneous form, I still have this g of x piece. So I need to find something that when I plug into the differential equation gives me that g of x over here. Now, in this type of solving method, we are going to essentially just guess and check on what g of x is going to be. G of x needs to be of the form that is given. Sorry, your p of x, your particular solution, yp of x, should be of the form of a polynomial, an e, a sine, or a cosine. If you have any of these for your g of x, we're not going to be able to use this method, or there would be other methods that you would need to look at. However, if g of x is of any of those other forms, we are good to go. All right, so here is an example of what we would do. I have y double prime minus or plus 4y prime minus 2y equals, and then g of x is a polynomial term on the right-hand side. So I'm going to use our constant auxiliary equation to say, okay, I need m squared plus 4m minus 2 to be equal to 0. I'm going to need to use the quadratic formula. And m equals negative 4 plus or minus the square root of, let's see, 16 plus 8, 24 over 2. This is 4 times 6, so 2 root 6 over 2, negative 2 plus or minus the square root of 6. Okay, so in my complementary function, I get c1 e to the negative 2 plus root 6 x, and then c2 e to the negative 2 minus root 6 x. The next piece that I need to go in and find is this right-hand side, because if I were to plug this in to my differential equation, then no matter what c1 and c2 is, this would end up being equal to 0. So I'm going to choose yp to be of the form ax squared plus bx plus c. And I need to know when I plug into this left-hand side, what combinations of a, b, and c end up giving me this right-hand side. All right, well, yp prime would be 2ax plus b, and yp double prime would be 2a. And so when I plug in to that left-hand side, I end up getting 2a plus 4 times yp prime minus 2 times yp, and I need this to be equal to 2x squared minus 3x plus 6. All right, so I'm going to go ahead and expand this. And then I can go ahead and just take this term by term and know that a must be -1 because that's the only thing, if I were to plug in, that I would end up getting 2 in front of my x squared term. Then I can also look at my terms here. So I already know this would be -8 plus -2b must give me -3. So if I add 8 and divide by 2, I get that b must be -5/2. And then I can do a similar thing so I know that -2 minus, okay, 4 times this, so -10, minus 2c must give me 6. So I have -12, 18, so c is going to end up giving me -9. And so here is my complementary function, and then I say that yp must then be -x squared minus 5 over 2x minus 9. And so that's going to be my final answer for this problem. All right, in example 2, I just want to look at a particular solution. Now, because sines and cosines have derivatives that are each other, right? If we go around like so. I actually, in my particular solution here, need to have both sine of 3x, but then cosine of 3x, because if I plug into our left-hand side, it's possible that I might have sines or cosines in my particular solutions, and then once I take derivatives, they cancel out, and then I'm just left with this right-hand side. So let's find this. Yp prime is 3a cosine 3x minus 3b sine 3x, and yp double prime is -9a sine 3x minus 9b cosine 3x. And I'm going to plug this into our right-hand side, or left-hand side. All right, so that will give us -9a sine 3x minus 9b cosine 3x. Now I'm going to subtract y prime. So minus 3a cosine 3x plus 3b sine 3x. And then I'm going to add and I need this to be equal to 2 sine 3x. Okay, so let's figure out what's in front of my sine here. So I have this one, and that one. So when I combine some like terms, I end up getting that -8a plus 3b must give me 2, because that's my coefficient in front of sine. Well, there's nothing I can really do here. It's not like this one up here. All right, so let's look at cosine. Okay, and then I know that negative 8b, if I combine those, minus 3a has to give me 0 because I don't have a cosine term over here. Okay, so then negative 8b equals 3a, and so a must be negative 8b over 3. I can then plug that in here. I get 64b over 3 plus 9b over 3, just kind of converted that, equals 2. So I get 73b equals, I'm going to go ahead and just move that over. And so b equals 6 over 73. I can then plug that back in to a, and when I do, I end up getting negative 16 over 73. My 6 and my 3 cancel, and I'm left with 2. So that's how I got the negative 16 over 3. And so notice up here in my answer that I actually have both sines and cosines, and when I take the derivative of those pieces based on my differential equation, I'm left with just the right-hand side